So one of the most interesting things about circuit analysis is that when you do a combination of two or more resistors either in series or in parallel, it often changes the geometry of the circuit in such a way that it opens up another combination that can be performed. We saw that actually when we did figure 4, where we combined the two resistors in series, and then that opened up a possibility in parallel that didn't previously exist. This is I call this successive combinations. And figure 7 really gives a good example of this. And this is going to be one of the most important skills that you can have as a circuit analyst. I know I keep saying that, but if they weren't really important skills, we wouldn't be introducing them this early in the curriculum. If you look here at figure A, you can see that we've already identified that the 6 ohm and the 7 ohm resistors are in parallel, and the 3 ohm and the 2 ohm resistors are in parallel. So we're going to go ahead and combine those together. So to calculate the 6 ohm and the 7 ohm in parallel, that'll be the product divided by the sum. 42 divided by 13 gives us 3.231 ohms. And that used to be, both of those used to be connected between the 8 ohm resistor and the bottom terminal. So that's where the equivalent resistor is now combined. The 3 ohm and the 2 ohm, the product is 6, the sum is 5, divided by 6 divided by 5 will give you 1.2. So you can see that I've simplified the circuit. It used to contain 1, 2, 3, 4, 5, 6, 7 resistors. Now it only contains 5 resistors. Oh, and by the way, before there were no resistors in series. But now you'll notice that the 8 ohm and the 3.231 resistor are in series. And by the way, the 5 and the 1.2 ohm resistors are also in series. So let's go ahead and combine those. Those combinations are easier. 5 and 1.2, you just add them, you get 6.2. 8 and 3.231, you add them, you get 11.231. And look here, now these resistors are all 3 in parallel because they all connect together on both terminals by only passing through wires, and junction points are fine. Branching points are no problem. So to calculate the resistance of these 3 resistors, I would take 1 divided by 4 plus 1 divided by 6.2 plus 1 divided by 11.231, and then I would invert that number, and it turns out to be about 1.999 ohms. So we've been able to reduce this circuit down from one that had 7 resistors down to one that has only a single resistor. And this is definitely going to improve and simplify the work that we have to do with this circuit. If, for example, if I had been asked to find what is the current leaving the 12-volt source, gosh, this is going into like some big complicated conglomeration of resistors. I have no idea. But over here, if you said, oh, what is 12 volts? What is the current leaving the 12-volt source? Oh, you know what? That's only being restricted by about 2 ohms. That's going to be about 6 amps flowing around that circuit. Now, if you said to me, what is the resistance inside any one of these resistors? I'm sorry, what is the current flowing through any one of these resistors? That's a harder question. That's for another day. But for right now, if you said to me, how much current is leaving that source? It's going to be right at 6 amps. It'd be a little bit more because this is a little bit less than 2 ohms, but it's going to be really, really close to 6 amps. So that's it. The thing about this lesson is to understand that when you do a series or a parallel combination, it often opens up opportunities to do future successive series and parallel combinations, which ultimately, if you do several of them, can reduce the circuit down perhaps even just to a single resistor.